Hi, my name's Bob Greenyer and I'm a volunteer with the Martin Fleischman Memorial Project. So, welcome this evening. I have another on the fly presentation. I've got most of it scripted out for you in my head, but the things are moving so quickly at the moment, and we've got lots of beautiful data coming in. Dave sent some samples from the bismuth bullet test to Alan Goldwater, and I will be hopefully knocking a quick presentation out on that next week. It's extremely exciting what we're seeing there. And also, I haven't got round to doing the Bin Juin Huang data, but that's exciting too. But given the fact that September is coming up, and I'm going to be meeting some people that have contacts in Japan, in Italy, I think it's important that we loop back to this Fukushima project, and the stuff I have to share with you tonight is really exciting. It is preliminary, but I had to do it tonight, and the reason I had to do it tonight is because on Tuesday I will be taking a look at the samples that we tested with HHO in Slobodan Stankovic's lab. I will be testing those at the CITEC, Central European Information Technology something Centre. I tried to do that on Friday, but Friday basically was completely taken up by looking at the Vega Valley. And again, it's incredibly exciting what we're seeing on the Vega Valley. Frankly, unbelievable, and I want to be able to go back to that again on Tuesday, and so I've actually doubled the session that we had on Tuesday. And I can't really push it any more than that because I have to do those two presentations for next week and the Italian conference. Anyway, thank you very much for taking the time to be here with me this evening. I hope what I've got for you will be exciting. Now, can everyone hear me? I'm very glad that Slobodan has been able to make it in the room, and maybe he can add any context. I have two video audio microphones on the go today. I actually have a spare microphone if the main microphone goes down, and if people can tell me whether the spare microphone works. I've now switched to the spare microphone, and this one should work regardless, and I will switch back to the other one. And this is the original microphone, and I have a backup camera which I'm looking at you on now. So today, if the camera or audio fail, we have got a backup and a backup. So let's hope that that doesn't happen. Okay, so fixing Fukushima '05, encouragingly consistent first data. And it's not a coincidence that I have calcium oxide there in the shot. Now, I've been talking a lot about oxygen and its paramagnetic nature. Well, actually, calcium on its own, unlike its compounds, calcium on its own also has a level of magnetic susceptibility, but nothing like oxygen. Anyway, calcium is one of the elements that we have shown over many experiments. It seems to be a target for fusion, and it also seems to be a target for fission. And I've described the fact that I believe that that is because it is Dec alpha. It's doubly magic. What do I mean by that? Well, it has even numbers of neutrons and protons, and both of them are doubly magic. And it's Dec alpha. It's 10 alpha particles, and as we know, this alpha particle structure is very stable. Okay, so I'm sorry, David Boutlier. I will talk about your bullet test. It is really exciting what you've seen in the data. Again, in his bullet test, we saw a lot of calcium. Anyway, it's great to have you here. And so, hi Dan, hi Gordon, hi Elias, hi Ron. We've got quite a good complement of people here. So thank you, Corky. Okay, so let's get to this. So if I go to the Fukushima 04 rather, which I published just prior to this, and we can go. If I can go, still haven't dealt with the slow machine, but that will be next on my roster of things to fix for you, so that we don't have tedious gaps in our presentations. Okay, so let me go here, and I need to go to fixing Fukushima '04. If I can get to it. and it's here. So at the bottom of this particular one here, I noted that I would be talking about the first and most critical test for fixing Fukushima. Goal was exposing calcium carbonate to HHO to see if it, 1, exceeded the required 1000 degrees centigrade to produce the cold neutrinos needed to promote inverse beta decay of tritium, as per Dr. Alexander Parkhomov's theory, and or to see if there were any signs that transmutation was occurring due to the formation of coherent matter ball lightning in line with my own understanding, so that we could have a reasonable confidence that it would be beneficial to deal with the wastewater at Fukushima in Japan. Okay, so I'm going to show you a video now of the first time that Slobodan and I ran the HHO generator, and the first sample was the calcium carbonate, the section that was cut. And I don't have the loopback audio through here, so I'm just hoping that the mic will capture the audio for you. And I am going to probably continue making my presentation in the background whilst you watch this little excerpt. So here we go. Hi, it's Bob Greenyer and Slobodan Stankovic, the MFMP, and Slobodan went out and got a new gas regulator and flashback arrestor today to replace the one that died after over 10 years yesterday, and he's got it there on his hose. And we set up a bunch of cameras here, and we are going to look first at the response of the calcium carbonate from Vietnam, and we have a lot of filters and things. So shall we give it a go?
Yeah,
Let's do it. Okay. All right, so it's down here.
I'll just start the electrolyzer. Okay, let's do it like this. We've got something like high output. Okay. So you can see
there.
Don't see.
Okay, do you want to bring it into shot? So there isn't much of a flame to look at as it goes.
Yeah, it's very. You can see the flame is here.
Mm-hmm.
I mean,
Yeah, that's good.
this is visible.
Mm-hmm.
So, okay. So let's start the. Ready?
Yeah.
Okay. I'll start smoothly
Mm-hmm.
to the to heat a little bit. This is really bright.
So I'm going to use the welding mask. I'm going to put it in front of the camera's lens here
Yeah.
and see if we can see anything through
So
it.
you can even.
Oh yeah, okay. So we can
closer.
not see a lot through there, but if I go like that, I'll focus in. And if we go and put the welding mask in front. So this is looking at that glow in a output of a welding mask. I'll take that off again so you can see what it looks like on the camera. Let's go in. So it really is very bright. Difficult to get across just how bright that is, but this is through the welding mask. So it's interesting. You do see that kind of zizzing that we see.
Yeah, I think it's a melting.
Okay.
Inside. Sometimes you have some bubbles inside the.
So we're expecting largely carbon dioxide to come off this, aren't we? Because when you heat calcium carbonate above 850 or something like that,
Mm-hmm.
it decomposes into calcium oxide.
You have heat temperature measurement just behind you.
Okay, let's see what we can do with that.
On the top. Left, down.
Oh yes, there's a gun here.
Yeah.
Let's have a look.
Let's try to find out where is the maximum temperature it measures.
Okay.
this
So
laser
at the
pointer-
moment,
laser pointer.
I'm gonna turn off the zoom on this. So I'm at home, kids. I've got this laser pointer heat measurement thing here, and we're going to first see what it is on the ground nearby, and then we're going to go in and try and see where. So it's about 800 and something degrees. Let's see if I can get it actually bang on.
Maximum is, I think, 500.
1,400, 1,600, 1,800. We just read.
Oh, we have more than 500 degrees here at the point, so that's completely
So
possible.
I'm going to try and get the laser pointer into the centre there. So 1,909 degrees it said there.
Around. But I think if you just go around and you will see the maximum temperature that can catch up. Maximum
So where does this go to?
maximum 500.
Oh right, we're well above that.
Yeah, sure.
So it can only measure up to 500.
Yeah, I didn't find one.
Well, it did 1,900 degrees just now,
Yeah, no, it's not 1,000. It's not possible.
isn't it?
1,000? No, it's a point something.
But, well, you got the emissivity on 0.95, which is pretty good for ceramic.
Yeah.
Um,
It cannot be 1,800.
Well, it does. Well, 1,000. Yeah, I'm reading it right here. In fact, if I go like that now, hold on. If I go on it now, because I can actually see it, now it's cooling down pretty quick. So I don't move. All right, you go for it. 3, 4, 5, 350, 320, 320, 306, 350, 380. 390.
Go to the left a little bit.
How about we tape this down so that the spot's already in the right place, because my hand's moving all over the place.
Yeah.
I'm over there and I move over here. 1,100, 1,500, 1,900, 1,993, 1,900. Okay, 1,983. So this is definitely at the temperature you would expect 1,936. So this is definitely at the temperature you would expect some cold neutrinos to form, which is interesting, wouldn't you say? So I think we'll leave that as our first experiment, and we'll try and get this so it's fixed in position, and we can get a proper top reading. But I think these only go up to 2,000 or something.
Yeah, 2,000. Sorry.
Yeah, so
Because I already tried with the aluminum oxide.
yeah.
And the aluminum oxide, it's melting about 1,990 degrees.
Yeah, I mean, aluminium oxide is just over 2,000, isn't it?
Yeah, but it starts already melting.
Yeah.
No,
So
it's-
the calcium oxide is pretty much still intact. I guess it definitely will have decomposed to lime now. And you can see it's more flaky, so it's lost some mass there. It's gone a bit fluffy. So I expect that's decomposed to lime. But in the case of lime, it's now just sitting there and it's getting hotter and hotter. And that is exactly what you want to do if you want to produce cold neutrinos. Okay, so that was the very first time we ran the calcium carbonate with HHO, and so you experienced it as I experienced it through the camera lens, trying to protect my eyes. And Slobodan had his steampunked goggles on for a close-up shot. Anyway, so what it showed was that you did get this limelight. Now, the problem with the pyrometer, the spot pyrometer with the laser, is that pyrometer, it was correctly set to an emissivity of 0.95. But if you go and look at the spec sheet, you will find that for the spot pyrometer, it will only go up to 500 degrees C accurately. if it has a thermocouple on it, it will go to 1,395, although some people quote it's 1,400, but then the thermocouple starts to fail. The problem with using a thermocouple, as Slobodan quite rightly noted again, when you are using HHO, is that the HHO interacts with the metals in the thermocouple and causes them to fail. And so you can't really use the thermocouple. The interesting thing is it has a range that goes up to that level. The other thing is that it did seem to go up to and beyond 2000. When it went over 2000, it kind of like stalled and kind of like almost like it went round and lost the significant digit and started showing hundreds of degrees again. But it never really went above, I would say, if we're assuming that's what it was trying to do, it never really went above 2,200, 2,300 degrees. And that may be significant. So what you can see, actually, if you look at this end shot here, is that the calcium carbonate, which is over here on the right, looks pretty much still intact. And as you move down, you get this slightly darker grey area, and then you get this kind of snowy white area with cracks in it. Now, what happens with calcium carbonate is that it breaks down into calcium oxide, and it breaks the carbon dioxide, it evolves from it. And for that to occur, it normally requires a temperature of around about 825 to 850 degrees centigrade. I just need to kill that, and then I can show you. Where's it gone? There we go. We go up here. We kill this, and then I can show you my slide, which is where, well, what have I done with my slide? Give me a sec. Oh dear. Where's it gone? Okay, right. It's back in the room. Press play. Can't work as fast as I can think. Okay. So I'm going to show you the chemical reaction here of the decay of calcium carbonate to calcium oxide plus CO2, and this is straight from the Wikipedia article. Releases carbon dioxide upon heating, called a thermal decomposition reaction or calcination to above 125 degrees C, 1517 degrees Fahrenheit for those people in the US and old school people in the UK. Actually, on the Wikipedia it says 850, and on the Wikipedia article for calcium oxide, it actually says it's 825. So I took the calcium oxide data from the Wikipedia for calcium oxide. But there is some interesting things to talk about with these temperatures relating to calcium oxide, and that will you will see more of that in a paper that I'm going to show you. But in the case of calcium carbonate, to form calcium oxide, commonly called quicklime, with a reaction enthalpy of 178 kilojoules per mole. So I guess that is the energy that you need to put in order to cause the CO2 to evolve. And I think you get this back if it takes the CO2 on board or whatever. Anyway, you can see down the bottom the structure, and it's basically for every calcium atom you've got an oxygen atom. And so it's very, very regular, and that might be important as we go forward. Now, what did we see in that video was that the temperature must, because we know from this image that it would appear, produced calcium oxide. The the carbon dioxide has evolved, which means that this had to exceed 825. So already we're out of range for the thermometer. Then if we look at the temperature, 850 degrees, that's not enough to produce cold neutrinos. You need to go over 1,000 degrees, and I can show you here in the slide, which I've shared many times, from Alexander Parkhomov, which is this one here, the production of cold neutrino slides. And down here below 1,000 degrees, this 850 degrees, we're not going to get any joy with producing cold neutrinos. And if we want to deal with that tritium if we're going to assume that Parkhomov's theory is correct, then we want to be exceeding this 1000 degrees centigrade. And ideally, we want to be 2000 or more degrees. Now, is there any way, other than this kind of bogus, unreliable data that we are seeing from the spot pyrometer, is there any other way that we can know that we are achieving this temperature of around about 2000 degrees? Well, I think there is a way, and that is due to the property of limelight itself. And so I did a bit of digging around, and I found a paper that I will point you to now, and we will be able to look at this, a couple of key points from it. And I think this will settle what's going on. So this particular paper is it is here. And this software works so slowly when it's doing this. Okay, all right. So here we go. And this is a PDF, and it is from 2012, and it is high temperature behavior of nuclear materials investigated by laser heating and fast pyrometry. It's actually a rather large document. I think how many slides, pages? It's got 240 pages, so it's basically a book. And it goes into a lot of materials that one might think are useful for nuclear reactors and so forth: vanadium, niobium, molybdenum, tantalum, tungsten, because these are refractory elements. These are and here we've got refractory compounds: calcium oxide, cerium dioxide, thorium dioxide, and uranium dioxide, and so on. And so interesting, they made a big feature on calcium oxide in this particular paper. And I'm going to go straight, by using the search term up here, to limelight. And if we go to limelight, we're going to read a bit about limelight, and this is going to tell us something very important straight off the bat. Okay. Optical properties. Calcium oxide exhibits a particular behavior when it is heated beyond 2000 degrees Kelvin. Then it emits a dazzling bright white light called limelight, or Drummond light. This behavior has been known since the 1820s, when Sir Goldsworthy Gurney, not Thomas Drummond, who is mistakenly credited with the discovery, discovered that certain metal oxides, including calcium oxide, emit shorter wavelength light when heated than would be expected if the emission were due to incandescence alone. Thermal emission of calcium oxide was used in high-power light sources, film projection, and illuminating devices without a physical explanation of the involved phenomena. In 1930s, this phenomenon, called candoluminescence, was ascribed to redox mechanisms. At the end of the 1940s, Soviet scientists explained the emission of oxides as specific equilibrium thermal emission of a solid, whose emittance is strongly dependent both on the wavelength and temperature. Sokolov et al. Suggested the existence of candoluminescence at a temperature of below 900 Kelvin for different materials, among which there is calcium oxide. Since in all Sokolov's experiments the temperature was lower than 1300 degrees Kelvin, Kubarov argued that those authors believed calcium oxide did not change in all the temperature range from 1300 Kelvin to the melting point, where it would behave as a black body. However, in Kubarev's experiments, sharp and evident changes were visible at 2000 degrees Kelvin. When this critical temperature value was reached, the calcium oxide emittance increased by a factor of about 10. Its emittance increased by about a factor of 10. That's an order of magnitude. And actually, here is the chart, and maybe I can zoom into that for you. So temperature dependence of calcium oxide emittance in Kubarev's experiments. Okay, so you can see it's about down here, which is looking like about 0.1 all the way down here, until it just goes over about 2000 degrees and it rockets up to 10 times the original emittance, and you see it up here basically flatlining up here. So what can we learn from this data that I have just shared you? Well, we can learn that we must be exceeding this 2000 Kelvin limit. That is very interesting, because that's also kind of what we saw on the spot pyrometer. There's a little bit more I want to read from this particular paper. But anyway, considering an emittance close to 1 at high temperature, Kubarev obtained a reasonable value of 0.1 at low temperature, which was in agreement with emittance values found in literature for other white oxides. The main result observed by Kubarev was the remarkable change of calcium oxide from a mostly transparent body to an almost ideal black body in a range of temperature from 2000 to 2000 degrees Kelvin. 2000 degrees Kelvin is around about 2000, just over 2000 degrees centigrade. This is kind of where it is going a bit wonky. Materials with this behavior can be called semi-transparent. This name is actually related to a low absorptance, high absorptance transition. As a matter of fact, the low emittance, low absorptance material is not only transparent but also reflective at the wavelength of interest. In the present work, which is this laser stimulation of these materials, a similar behavior was observed on calcium oxide under different environmental conditions and different types of laser pulse. The presence of plateau at the beginning of the heating process was observed. And here you go, you've got 2100 Kelvin up to about 2288 Kelvin. And this is around about, the sort of midpoint of this would be somewhere in the around about 2000 degrees centigrade. So here we have a confirmation that probably we are getting to around about 2000 degrees centigrade. And so what does that mean for us? Well, actually this particular book goes to extreme detail to establish the melting point of calcium, which is also relevant, but not really relevant to what we're talking about in our presentation here. So I think I can go to this slide, which is on page 166, and they have this freezing plateau here. So basically, they've turned it into a liquid up here. Sorry, I've zoomed the wrong thing. I should be clicking on that and zooming that. There we go. So they have heated it up to a point where it's gone into a liquid phase. Oh, I'm actually looking at the wrong thing here. Uranium oxide. Anyway, it is. They found that the temperature was quite a bit higher. It's in the 2650 or whatever that I had on my cover slide for the presentation today. Something 2570 degrees C is the what it said on the cover slide. But anyway, that's not so important. What's important to me is that we must have exceeded this 2000 Kelvin, but even probably up to 2300 Kelvin, so around about 2000 degrees centigrade. And what does that mean for our potential cold neutrino production? Well, if we look at the chart that I showed you earlier, and it's here, if we look at the 2000 degrees, you've got about 10% of the matter that is participating in the production of cold neutrinos. Now, the 1000, even if we're only achieving 2000 degrees Kelvin, that is approximately the same temperature that Alexander Parkhomov's 225-day reactor was operating at. It was just over 1700 degrees C. And so certainly this calcium oxide with HHO is a fast track to the kind of temperatures that Alexander Parkhomov was using in that reactor. And as we know, that reactor was producing a plethora of transmutations. We observed it in our data, and I think he sent samples to about 6 or 7 other labs, and we all observed transmutation from that particular reactor. So from the point of view of being able to produce cold neutrinos, assuming that Alexander Parkhomov's theory is correct, I think we can argue pretty conclusively that it meets the criteria for that. Now, what else can we see from what we did on that day? I have another video for you, so let's see if I can dig that out and show it to you. Okay. So the second video was taken shortly afterwards from the one that you've just seen, and we will play this through. Give me a sec, line that up with that. Give me a sec, it's playing. I'm here with Slobodan, and unfortunately he's got a free version of this spectrum analyzer, and he says that it only gives you certain lines that it can identify, but it identified in the visual spectrum the argon line at 610.12, and in the IR it identified also the argon line at 1330.23. And I said, well, let's crank in the H and calcium into nanosoft.co.nz, and if you do that with neutrinos, so a neutrino coming in on the left side, so that's a neutrino that would be synthesized, you end up by seeing helium and argon 40 being produced, and that is the most likely reaction with a yield of 1.507 MeV. So is that interesting? I don't know. Okay, so my other camera has gone, and we're back. We're on to our backup camera. Look at that smooth transition from one camera to another. Okay, so what I'm going to do now is I'm going to use the Alexander Parkhomov reaction tables that were built by Philip Power with my guidance. Absolutely fantastic tool. Thank you, Philip, again, and thank you, Alexander Parkhomov, for providing those. And what we're going to do is we are going to put in the what we just saw there on the table. So we're going to do a 2-to-2 reaction. So let me see if I can work how to do this on here. So I'm going to where are we? I'm going to put in H. Don't worry, I will switch screens in a second, and calcium, and we will see what we get there. Okay, so here we go. So if it's going to do it, I'm going to execute my query. Okay, so what I've got for you here, I'm going to zoom in, and what did I do there that I didn't do? I've put in fusion, haven't I? That's why. Fusion! It's 2-to-2 reaction, isn't it? Okay, let's try that. Okay, so this is what I did live on the camera there when I was with Slobodan in his lab. So essentially, you have hydrogen, which is in our HHO, a isotope of calcium, not a very big isotope of calcium. Let me just check that. It's not a very common isotope of calcium. And we are getting, so calcium 43 is, it's 0.14%, 145% is not a lot. So anyway, we have a proton going with calcium and producing helium-4 and argon-40. But it is the most energetic reaction of the protons interacting with calcium reactions, and it requires a neutrino. So is this an indication that we are able to produce neutrinos? That would be great if it was, maybe not. But it's the next observation which I found really, really rather more exciting. And so I'm going to play another video now, and we're going to look at the basis for that afterwards, I believe. And let's see what we can do now and see if things don't fall apart more than they have done. Okay. Give me a sec. Oh, excellent. It's great to have Henk, Dave and Slobodan all watching. This is absolutely fantastic. Well, I'm hoping to get out and work with Henk sometime after I have been to Italy, and I can tell you now that I'm hoping to look at the copper pipes that were exposed to the Vega experiment, where they had large ball lightning segments taken out. So anyway, let me just play this video here. I think this is the one I want. I hope it's the one I want. Let's see if it is. Okay, far away. So I just wanted to show you something else. And that's why I've got this microscope in my hand. And we are going to look at the area which was exposed to the HHO. And if I come over here, you'll see that on the edge, it's really rather glassy. If I can get in here without breaking anything. Can't get in here. So this is the edge, and look at that. It's really rather glassy. Now, I'm sorry for the shaky vision, but what is that? Okay, I've just paused that because what we're looking at here is something that appeared strikingly glassy. This was the area that was most exposed, and in fact that there are other videos, and these will all be published when I can get round to processing them. But the particular piece that you see here was the corner that was most exposed to the HHO, and it did look very, very glassy. And in fact, when we were starting to look to take samples of this, it was very, very hard. And I'll just continue playing this. That there. Is that some sort of silica? Has it got magnesium in it? What's going on? If you come over here, you can see the kind of more flaky nature, and there's some fragments down on the ground that we may be able to get a good shot of. Yeah. There's a fragment here we can look at. You see how that fragment there, it's on an alumina background, but I can get that fragment in the centre of my field of view. There. So this is the flaky. Okay, so what you're seeing on the this particular shot here, this is a piece of the calcium oxide which has lost the carbon dioxide, and it sort of dropped off. It's not the same as the kind of very glassy hard thing that was in the area that was most exposed to the HHO. So I'll just play on. Calcium oxide on the alumina, which is the background that you're seeing here, this foamed alumina. And if you go here, this is something different. It's glassy. It's all used to get. Okay, so I hope you can see that that is very, very much different. And the interesting thing about this is that the calcium carbonate, there is a form of it that is like crystalline, but it was extremely hard, this thing that was left over. And so I was talking with Slobodan that I felt that this probably could be silicon. And I just had a gut feeling that it could be silicon. And anyway, I will run through some things now, and hopefully we'll find out that we found something rather interesting. And at the moment, we don't know. But on Tuesday, we will know. But we do have some interesting data. So one is we have a temperature that can get to the point of potentially creating cold neutrinos. So that can affect not only decay, but it can stimulate interaction between nucleons in a long-range way. And then we know from other HHO in terms of Mars gas that we have been able to create microball lightning, and in the case of the 10 yen coin, the snowballs on cobblestones, we have got the oxygen on the copper oxide to cause the two oxygens to come together, O2, and fuse to sulfur. And this is observed with ball lightning, and I've been talking about this. It's been observed in nature as one of the things that happens when ball lightning explodes. Okay, so this is all kind of lining up. And so what I'm saying is we have shown that oxyhydrogen gas in the form of a Mars gas can create ball lightning, which I believe, and there is other supporting evidence in the literature, that it can cohere matter and it can cause electronuclear collapse. From Matsumoto's work from the late 1990s, where he was doing his lead in potassium hydroxide in light water and just using 200 volts and a little bit of AC. Why is the AC important? In my view, the AC creates oxyhydrogen gas and it's immediately burnt, and he creates microball lightning, and that causes transmutation, electronuclear reactions, including fusion, fission, and electronuclear collapse. So you've got the whole smorgasbord of things going on. So I believe that we already have shown that you can fuse. Are we seeing fusion or exchange reactions in there? Let's find out. So let's kill the video here. And I'm going to show you the next video slide here. Now I actually have to build my slides on the fly here because I didn't finish the presentation, but we're going to finish it together. Okay. So, from the elements database in nanosoft.co.nz, here are the isotopes of oxygen and calcium. And so you've got three oxygen isotopes, 16, 17, and 18. And 16 oxygen comprises 99.759% of natural oxygen. So basically, almost all oxygen that exists would likely be from 16 oxygen. You know, the vast majority of oxygen is 16 oxygen. In the case of calcium, you've got a whole bunch of isotopes, and this is great. This is really good when we want to, if I'm actually showing the slide here, so sorry. You have 16, 17, and 18, and you can see that 16 oxygen is 99.759% of natural oxygen. So this is the one that's most likely to take a role in LENR because it's the most abundant. The second thing is calcium has 1, 2, 3, 4, 5, 6, 7 isotopes, with 40 calcium comprising 96.97% of natural calcium. And so, the reason that I considered using calcium in this particular solution is that calcium is what LENR likes to fuse to, and it's what it likes to fission from and going to calcium. Now, if you have calcium 40, which is, as I said, 96.97%, there is a huge amount of neutrons that you can absorb from your gas, 1, 2, 3, 4, 6, and 8, before the calcium becomes unstable. In fact, technically, calcium 48 is unstable, but it has a half-life, which is pretty sizable. Okay? And so the fact that we have an overabundance of neutrons in tritium, then this could be effectively something that could capture neutrons if it can't do much else. Well, I've already talked about the fact that the tritium reaction is one that actually goes 40 calcium, the most abundant calcium, plus tritium goes to helium by extracting a proton from the calcium and potassium-39. So you get a helium nuclei, this would evolve, and you have the potassium-39, which is the most abundant isotope of natural potassium. So in my view, with my understanding, the nature, what you see in the crust is what nature wants to do, because this is a natural phenomenon. It occurs in cavitation, it occurs in electrical storms, it occurs in tectonic plates, in volcanoes, all kinds of places, in my view, this occurs. And so what you're seeing in the crust is the net result of 4.5 billion years of this process being ongoing. So it would not surprise me if you had tritium taking a proton, making a helium atom, and producing potassium-39 from the combination of tritium and calcium-40. Anyway, so what might we expect it to produce if we were to take the most abundant 16 oxygen and the most abundant 40 calcium? Okay, so the most abundant oxygen and the most abundant 40 calcium. Bananas, maybe. Yeah, bananas have potassium 40 in them, not potassium 39. Okay, so let me just, I'm going to build the next slide whilst you're waiting. So talk amongst yourselves. If you've got any questions, now would be a good time to ask them, whilst I am chucking in a new slide here. Is everyone with me so far? This is so slow. Anyway, the backup audio and the backup camera is working today, so woohoo! Helium-3 is not a common isotope. Yes, helium-3 can be produced, but it's unlikely, and so it probably won't. Simon, you're going to be really loving what I'm just about to show you. And thank you very much for your kind words in your own channel. Hopefully we're going to be knocking the back of this. I hope you got a chance to see the ball lightning presentations I made recently. I was absolutely shocked and stunned and delighted when I read the December 1993 submitted, May 1995 published paper in fusion technology by, basically funded by the US Air Force, saying that if we could produce technologically produced ball lightning and have it free floating, I mean, they literally say that then this might enable, with the known 1 centimeter size ball lightnings and natural ball lightnings, and we know that we have achieved them in the low microns, so they're targeting, if we have a device that can produce them stably at 1 centimeter, then we can create very small devices for a range of applications, and I believe that is what we are on the verge of doing. It's very, very, very exciting. I cannot imagine anything more exciting to be working on in this universe. Hopefully there's other universes out there we can enjoy when we've gone, but this one, it's all there is now, and it couldn't come at a better time for humanity, I would suggest. Right, so here is the result for the fusion of 16 oxygen and 40 calcium. If you go to nanosoft.co .nz, and you go to the fusion. And so what I'm saying is I'm specifying A1 as 16, so that's only that I'm only looking at oxygen. In this case, I'm not looking at neutrinos, so I'm looking at an electronuclear reaction as per Matsumoto. And the A2 is 40, so I'm specifying the most abundant isotope of calcium. And that is calcium, because if I specify an A2, it'll also pick up argon and potassium that have an A2 of 40 as well. Oops, didn't mean to do that. Let's play again. You can look at my mugshot while my computer warms up. Right? Okay, so and you know what? If you fuse these two together, what do you get? You get silicon 28 and dun, da, 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 silicon 28. Wow, that is amazing. So you know what you do? Let's look at silicon. You have 3 isotopes of silicon: 28, 29, and 30. And silicon 28 is by far the most abundant, 92.21% in the crust. So this is the most likely thing that will be produced, okay, in my view, with my understanding. And it's 3.4 million electron volts. So if you get 2 H's and you fuse them together, I think it's something like 4.52 electron volts. This is 3.4 million electron volts. This is a lot of energy. And it's aneutronic. And the energy will be split between these two. So it's 1.567, 1.7 million electron volts kinetically on each of these silicon 28 nuclei. And that will produce quite a lot of heat. So there we have it. And this beautiful structure of calcium lends itself to this reaction beautifully, because every calcium has an associated oxygen next to it. You see, it's like a checkerboard. And so why would it not do what you are seeing here? Well, let's have a look at any other potential reactions, and I will take another pause. You can ask some other questions whilst I build another slide, and I look forward to seeing what you have to ask. So give me just a second and I will build the next slide. Fortunately, I've prepared the underlying data. Otherwise it would be tedious. Anyone got any questions? We're building up to a bit of a punchline here in a minute, so... Okay, I'm going to build 2 slides. So, anyone got any questions? Can you still hear me? Are you bored yet? Slobodan, great, because I think you know where the punchline's going. but we shall enjoy, or not, the confirmation, or not, on Tuesday. You've probably saved yourself 40 minutes, Dan. Okay. Just a minute or two. And I'll be done. One last slide. Slobodan, are you saying you sent it right now or previously? Okay, yeah, we're good. Don't worry, I'll capture it. It's why I changed what I was going to say tonight. There's a roster of things that are also freaking awesome, but given the fact that I will be looking at the sample that we made. I'm talking to Slobodan. The sample that we made on Tuesday. I think it was necessary for me to get this out the door. Okay, so this is what I showed previously, and this is taking the most abundant most abundant isotope of oxygen and the most abundant isotope of calcium, and you get a fusion event, a nucleon exchange event leading to the most abundant isotope of silicon in abundance with 3.4 MeV. But what if we look at all isotopes of oxygen and all isotopes of calcium? What is the result when we are thinking of getting also silicon? Well, oxygen 18, rare. Calcium 40, common. But this is rare because oxygen 18 is rare. But what do we get? Silicon 28, silicon 30. If we start with oxygen 17, rare. Calcium 43, rare. Really rather rare. Silicon 30, silicon 30. Oxygen 18, rare, 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 rare. So the first reaction, i.e. the reaction that has the next most after all of these rare isotopes of oxygen, is oxygen 16 and calcium 40 leads to silicon 28 and silicon 28. This is, for me, the money shot in terms of these reactions. And as you go down the table, you get other silicon isotopes. But this is what you find, but it's all rather special. Well, what happens if we allow look at this in a slightly different way? If we look here, we have got what do we got here? So the first one is where we're just looking for silicon in E4. This is E4 line. What if we look for any elements in the E4 line? Well, we have oxygen 16 here with calcium 44, produces helium, and iron 56 with 11.988. That's quite a lot more energy than that 3.4. Then we have oxygen 16 with calcium 46, and goes to iron 58 and helium. And then we have oxygen 16 plus calcium 42 goes to helium and iron. So this would imply that we would see some iron potentially in the material we end up with, and some helium in there. But why would we not see potentially a strong line? Well, it might be that we don't achieve the ionization of the helium, and it might be that the actual production is low. Why is the production low? Because 44 calcium, 46 calcium, and 44 calcium, sorry, I've got that wrong. That should be, I'm going to correct that right now. It should be 44, 46, and 42. So let me just correct that. You can go back to my mugshot. 46, 44, and 42 is what it should say, if I'd done it correctly for you. Here we go, and I'm going to show it to you now. Da-da, da-da, da-da. Okay. 46, 44 and 42 is 2.7% of natural calcium rather. And so I don't see this as playing a massive role. Now, if we go to the next two, I put them in orange here. And the reason I put these in orange is because they're using 44 and calcium 46, which are already up here using oxygen 16. So this is a much less energetic reaction. So in my view, in coherent matter ball lightning, it would prefer to do the 44 reaction up here, which is the number 1 most energetic, and this one, which is the number 2. So these isotopes would be used up. So this doesn't occur. So what is the next one that occurs which has available isotopes? Well, it's this one, our old friend, oxygen 16 and calcium 40, producing silicon 28, silicon 28. And then we have 43, which is not used up here, which is oxygen 16 plus calcium 43 goes to silicon 29 and silicon 30. And in between these, you have all of the isotopes. In fact, you create all of the isotopes of silicon just with these reactions. And then if you go down the table, these are all isotopes that are participating in the reactions above. Now, the interesting thing is, we'll go back to our crust here, our abundance of elements in the crust, and we can see oxygen is the most abundant element in the crust, and calcium is the number 5th, 1, 2, 3, 4, 5 most abundant element in the crusts. And what we're seeing is here, if you take calcium oxide and you go through a coherent matter process, it would appear that we would synthesize silicon and iron. But we don't know that yet, do we? We have a temperature that gets to a point that could produce argon, because you need that neutrino to produce that argon that we saw in the spectral lines. But that isn't the only spectral line we saw. Remember I said to Slobodan, I think this might be silicon. It's very, very hard. It's not crumbly like the calcium oxide or the calcium carbonate. It is very hard. And so I think this probably could be silicon. Well, guess what was sent to me by Slobodan? Check out this spectrum. So you have your nanometers or nanometers of light, I guess, from about 180, I guess, maybe. Coming up here, there's nothing. This is on the 0 line. And you start to get some action around here. This might be the sensitivity of the spectrometer. And it comes up, and it comes up, and it comes up, and it reaches a peak here of, I don't know, about 100, 200, under 300. And then here, boom! Boom! A huge silicon line here. A huge silicon line. Look at that silicon line. What is making all of that silicon? What is making all of that silicon? Could it be that we've got oxygen 16 and calcium 40, the two most abundant by far elements in the calcium oxygen 1-to-1 ratio, producing 1-to-1 ratio of silicon 28 to silicon 28? Is that what's happening, which is producing this massive silicon signal? Is that what's happening that's causing the production of something that looks like glass? It looks like glass. Is it glass? It might be glass. It might be silicon dioxide. It might be forming quartz. And what is silicon dioxide? Well, silicon dioxide is the most abundant element in the Earth's crust, or compound. Like it's basically what a lot of the crust is made of. It's the two most abundant elements, silicon and oxygen. There we go. So I thought that was quite special. We started off by having some material here, calcium oxide, synthesized from this Vietnamese sourced. Thank you to my darling wife and her friend in Vietnam that went to the quarry I had highlighted and got some sample sent over. And when this is heated up using the HHO, it would appear that it gets to a temperature of around about 2000 plus degrees centigrade. And we showed by using this particular data from, let me get it up, I will get it up for you. Let me find it. We had a bolometer, a spot parameter rather, looking at the sample, but in fact that wasn't good enough for me because there was a potential that the device wasn't reading anything that was correct. But by looking at this particular research from 2012, it detailed something very, very useful. And that is that, if I go to it now, they talked about limelight, and they talked about the fact that they established limelight has to occur at around about 2000 Kelvin. And they got this graph from a guy called Kubarev, and you can see it has to go over 2100, 200, 2200 or something Kelvin, and it shoots up, and you get a 10 times change in emissivity. And you know what? We saw it get super bright. We saw it get super bright. I shared that video at the beginning of this presentation, and it's so bright that you can see it clearly through a welding mask, and it's quite offensive. And this is a thing called limelight. So we know that we are achieving something that's close to the temperature that Parkhomov had in his 225-day reactor, and we know that that had large-scale transmutation going on because that was observed by us using Magic Sound Lab. Thank you very much, Alan Goldwater. And we established that, but also the data was supported by, I think, 6 other labs that looked at samples from that. And they are confirming that in their experiments, they had these laser experiments, they were raising the they were producing this limelight in the temperature range 2160 to 2288, and this is around about 2000 degrees centigrade. And if you are operating at 2000 degrees centigrade, well, what does that give you? Just to go over it again, that gives you this, which is around about 10% of your matter is able to produce cold neutrinos. And we went through calcium carbonate, decays to calcium oxide, and that has this structure. And that if you take those two most abundant isotopes and you do an exchange reaction, you produce silicon-28. If you look at all of the elements, sorry, all of the silicon element 4 column silicon producing reactions with all isotopes of oxygen and calcium, you get just silicon across the board in both panels. But if you look at it for all reactions, for the rare isotopes of calcium, you see the production of iron and helium, and for the common calcium-40, it's the next, the first available reaction is the production of this silicon. You have calcium here and oxygen here, and it would seem from this reaction that we may see some iron, and so potentially we will see some iron in there. And if you go to the last slide, we have this huge silicon line from the reaction. So the coup de grace in this is if in the analysis on Tuesday we observe silicon, and it would be an added bonus to see iron. If this is the case, then we have a system that is easily proving transmutation, and it is at a temperature that can produce cold neutrinos, and this, in my view, would set up the perfect environment for dealing with the tritium at Fukushima. So I'm putting it out there before we know the real answer, but I think that this data is pretty pretty strong, given the fact that, and I will bring up the video for those that missed it. Let me just find that. I'll find the video for those that just missed it at the beginning of the presentation, because it is important to observe that particular glass-like state of the calcium carbonate. So with two videos which are really important. I think it's the calcium carbonate producing this hard structure, and I think the one where you can see that it's producing the limelight. Okay, so we'll pull up those two videos and we'll just run the relevant parts of those. Give me a second. Okay, so let me find the relevant part of this.
So let's start it. Ready?
Yeah.
Okay. I'll start smoothly. So the to heat a little bit. This is really bright.
So I'm going to use the welding mask. I'm going to put it in front of the camera's lens here, and see if we can see anything through
so
it.
So you can even.
Oh yeah, okay. So we can not
see
see a lot through there, but if I go like that, it'll focus in. And if we go and put the welding mask in front. So this is looking at that glow in the output of a welding mask. I'll take that off again so you can see what it looks like on the camera. Let's go in. So it really is very bright. Difficult to get across just how bright that is, but this is through the welding mask. So it's interesting. You do see that kind of zizzing that we see.
Yeah, I think it's a melting,
Okay.
inside. Sometimes you have some bubbles inside the.
So we're expecting largely carbon dioxide to come off this, aren't we? Because when you heat calcium carbonate above 850 or something like that, it decomposes into calcium oxide.
You have heat temperature measurement just behind you.
Okay, let's see what we can do with that.
On the top.
Okay, so the thermometer showed temperatures exceeding or knocking up against, if I find a particular image, let's find it, 1431, I think somewhere around there. No, 1936, 1937 there. Okay, 1981. Okay, 1936. Okay, so like I say, the calibration is only valid up to 500. It works with the thermocouple up to 1400, but it seems to not go out of range until it exceeds 2000. But because we know we are getting limelight, this extreme glow up here, we know that we're probably exceeding 2000 degrees C, and at that point, 0.1 i.e. 10% of the matter is participating in the production of cold neutrinos that can affect, because of their wavelengths, they're in microns to millimeters, they can cause the interaction of large numbers of nucleons, and also potentially cause beta decay of tritium. So the last video that I would just want to go over again is the video here. Just close that one down, where I look at it with the Dynalight microscope, and you can see it here.
But I just wanted to show you something else, and that's why I've got this microscope in my hand, and we are going to look at the area which is exposed to the HHO, and if I come over here, you'll see that on the edge, it's really rather glassy. If I can get in here without breaking anything. Get in here. So this is the edge, and look at that. It's really rather glassy now. Sorry for shaky vision. But what is that?
Okay, so this is the glassy substance that when I saw, oh, I thought, I think we might be creating something that is silicon here. And I hadn't looked at the reaction tables. I didn't know exactly, and we hadn't looked at the data from the spectrometer at that time. But it was very clear when after we'd done a series of experiments, and I will share those videos, when I was taking those samples, those pieces were really, really hard, and they just reminded me of a fraction from a broken glass, you know, broken glass window, like you were picking up a fragment from a shattered window. And so there we go. That's what I have for you today, and so it's a relatively short one for me, and I'm sure you're happy with that, especially those that had a wedding on the weekend. And so thank you, Slobodan, for sending over that previous data for the spectrometer. That was helpful for me to decide what I was going to present today. And thank you for being patient with me today whilst I finished the presentation in the real time for you whilst we were working at it. And so this is the money shot of the day, I think probably we can safely conclude, is that, let's go here, the isotopes of oxygen and calcium, which are the vast majority of calcium oxide, which is a 1-to-1 ratio. Could it be that they are doing a nucleon exchange and doing silicon and 28? And why is this important for me? Well, I will do the reaction that I hope that we can achieve with Fukushima if we get the opportunity to go there. And I will do it again live here so that you can see. So what we're saying is, if we can prove that hold on, I have someone in the room. Don't go away. Nope, they're okay. So we will do this reaction here right now. If I can find my, not that. This, give me a second. Yeah, so my point being is that if we do show that we are having exchange reactions in this silicon oxygen 16 and calcium 40 to silicon 28, then that is just perfect for what we want to be doing, because we want another exchange reaction. So let me just make this full screen and I will do the exchange reaction here. So I am on 2 to 2. You see up here in the top left hand corner, 2 to 2, and I will go down and I will put in, what am I putting in? I am putting in tritium. So we want element 1 tritium. So we want to put in a T. And here we actually want calcium, but we'll leave it calcium for all isotopes of calcium. And we will see what we get. So execute query. And what do we get? The first tritium 3 plus calcium 40 goes to helium plus potassium 39. And look at that. It is 11.477 mega electron volts. Why is that important? Because you know what? It's a lot more than this reaction. This reaction here, which we've been talking about. If I can find it again, let me find it. Oh dear. Give me a second. So it's 11 point, what was it? Yeah. We are trying to see if the exchange reaction between tritium and calcium-40, which produces a proton, and calcium, sorry, not that one. The first one, between tritium and calcium-40, it produces helium and potassium-39, the most abundant isotope of potassium, 11.477. So we know, if we can see silicon, we know exchange reactions, in my view, are going on. And why would it be important? If I press play on here, you see why my machine runs slow now. There we go. This reaction is only producing 3.4 MeV. So if the calcium-40 wants to react preferentially to give the ability for the exotic vacuum object, the microball lightning, the itonic cluster, to fit into the smallest box possible, is it going to want to react with the oxygen-16 it's got available, or is it going to want to react with the tritium that's available? Well, I would argue that it would like to react with the tritium that's available, and the reason I would argue that is because it's going to be gaining a lot more energy. And what does that mean? It means it's fitting it into a smaller box, and so there is the reaction. So I think that if we see silicon on Tuesday, or iron and or both, in the sample, then I think that we have done sufficient proof to have a very, very good argument to put this forward as a proposal for fixing the tritium-laced water at Fukushima. And with that, I thank you for your time. I will take questions. It doesn't really matter whether it produces energy or not, Axel. The important thing is that we can get rid of the tritium, and we can do it in an aneutronic way, and we can produce stable isotopes that can be used later. And if we can get 11.7 million electron, or 11.477 million electron volts at the same time, we can make this thing self-support itself. Gordon, a coherent story of coherence and nucleon exchange that is in full agreement with what is found under our own feet in the Earth's crust. Yes, it's fully consistent. That's kind of what I said at the beginning of the presentation. My comment for the title of the presentation was encouragingly consistent data. Yeah, I extend my personal thanks to Slobodan for taking this challenge. This I would have liked to have done last year with either Amasa or Brown's gas, and in whichever case it was, I would have wanted to take Slobodan with me, but because of the sniffles, that was not possible. So we had to find a way to do this work, yes, it was not pleasant, but going there and back and the difficulties with getting things running, we overcame them. Slobodan worked through his problems with his teeth, and we battled on, and I think that this test already is well worth it. If we see that silicon or iron on Tuesday, it's fantastic. So almost the only way is down from this point, but if we see silicon in there, it's just going to be fantastic. Now, bearing in mind there's probably some silicon in the starting material, and we will be looking at it too. So I've given the operator at SciTech, I've got a sample before and after, so we can see the ratio of compositions, but we've got to have an adequate explanation for why this produced this incredibly hard structure that looked like it was silicon dioxide, and we have this huge silicon peak. So yes, as Slobodan says, it was alumina. In fact, if you caught the video, the first video, I mentioned, or what the one where I'm using the microscope, I'm mentioning that that underneath it is alumina oxide rather. Corky, yes, it's 130, roughly 130 degrees C, but we know that when you add carbon from whatever source into the gas flame, it increases its temperature. Could that be, in fact, that is one reason why I chose calcium carbonate, but that rapidly decomposes. So the reason carbon's in there, I kind of felt this is like the perfect thing, because the carbon is in there enabling the calcium carbonate to get up to the temperature which it decomposes, and it only leaves calcium oxide, and calcium oxide has this interaction where it produces these very high temperatures that then yield this extremely intense light. Yeah, so yeah, this is really something I can't wait for Tuesday, but I kind of wanted you to be like there for the excitement or the disappointment, so it had to be this presentation today, and I'm sorry for the other fantastic data I've had from various people, from various experiment threads that are ongoing, because they are equally amazing and consistent. But you know, so thank you for Bin Jun Huang from Taiwan University. I'm sorry I didn't get that. I wanted to do it before this Sunday, but I didn't get time. And I'm sorry for the fantastic data that we got out of the bismuth bullet impact tests, and I will look to explain that as soon as I possibly can. In fact, both of those data sets, and when we've done a little bit more, I might not be able to stop myself from presenting the incredible thing that is there on the Vega Valley. But I want to leave this presentation all about this particular subject today. I like it, Gordon. Rock on. Very good. I like your play with words there. I'm mentioning energy production because if it can produce that as energy, i.e. the particles come out with that shared 3.4 million electron volts. So your oxygen 16, your calcium 40, they do a nucleon exchange reaction and they come out as silicon 28 and silicon 28, and they can come out and kinetically with 1.7 each mega electron volts of kinetic energy, then that could produce energy and so forth, and loop that round. Certainly it's producing intense light, and maybe that would be something that could be utilized partially to offset the energy input. But actually over and above producing or removing the tritium, that is the most important thing here. So you almost wouldn't want to take too much heat away, because you want that temperature in situ to produce the cold neutrinos to stimulate the tritium decay. So I think this is going to be it for me today. I've got an 8 AM start at SciTech for the longer session, and we're going to bring sandwiches and everything, so everything's ready. So we just go straight through, and so I'm hoping to get through a number of the samples that we have from testing with Slobodan, and from some important Vega experiments samples, and some other random experiments that have been done over the years that I wanted to have a look at. I don't know how much we're going to get done, but the calcium carbonate that is now calcium oxide and potentially maybe silicon dioxide, that is for me the first on the roster of experiments to look at. So thank you very much for your time, and I will see you in the next video.